For centuries, physicists relied on Isaac Newton's laws of motion and gravity. These laws worked well for most everyday phenomena. They accurately described the motion of planets and falling apples. Newton's universe was orderly and predictable. Time was absolute, ticking at the same rate for everyone, everywhere. Space was a rigid stage where events unfolded. Then came Albert Einstein. Einstein began with a simple yet profound observation. The speed of light in a vacuum is constant for all observers, regardless of their own motion. This idea had mind-blowing consequences. It meant that space and time were not absolute, but were intertwined. They were relative, meaning their measurement depended on the observer's motion. Imagine you are standing still and shine a flashlight. The light travels away from you at the speed of light. Now imagine you are on a spaceship traveling very fast and shine the flashlight again. You might expect the light to travel away from you at the speed of light plus the speed of the spaceship. However, this isn't what happens. The light still travels away from you at the speed of light, no matter how fast you're moving. This might seem impossible, but Einstein realized that something had to give. The constant speed of light meant that our measurements of space and time were not absolute. Instead, they had to change depending on our relative motion. This led to the strange but true phenomena of time dilation and length contraction. Think of space and time as a unified fabric, like a giant trampoline. Massive objects like stars and planets create dents in this fabric, which we experience as gravity. The faster you move through this fabric, the more you warp it. This warping affects your measurements of both space and time. Perhaps the most famous equation in history, E=mc2, emerged from special relativity. It describes the relationship between energy, E, mass, m, and the speed of light, c. The equation tells us that mass and energy are interchangeable. A small amount of mass can be converted into an enormous amount of energy, as seen in nuclear reactions. This equation has profound implications. It explains the energy source of stars, the power of nuclear weapons, and the possibility of interstellar travel. It also suggests that even empty space is not truly empty but seethes with potential energy. One of the most baffling consequences of special relativity is time dilation. Time slows down for objects in motion relative to a stationary observer. The faster an object moves, the slower time passes for it. Imagine two identical clocks, one on Earth and one on a spaceship traveling at a significant fraction of the speed of light. When the spaceship returns to Earth, the clock on the spaceship will show less time has passed compared to the clock on Earth. This difference in time is not an illusion. It is a real consequence of the nature of space and time. Objects in motion appear shorter. Another bizarre consequence of special relativity is length contraction. Objects in motion appear shorter in the direction of their motion relative to a stationary observer. This effect, like time dilation, becomes more pronounced as the object approaches the speed of light. Imagine a meter stick flying past you at nearly the speed of light. From your perspective, the meter stick would appear shorter than a meter. This doesn't mean the meter stick has physically shrunk. Rather, it reflects the warping of space and time due to the meter stick's high speed. The universal speed limit. Why we can't go faster than light. Special relativity imposes a cosmic speed limit. Nothing can travel faster than the speed of light. This is not just a technological limitation, it is a fundamental law of the universe. As an object approaches the speed of light, its mass increases infinitely, making it impossible to accelerate any further. While we can't exceed the speed of light, special relativity hints at the possibility of bending space-time to create shortcuts known as wormholes. However, the existence and practicality of wormholes remain purely theoretical. Einstein's Legacy, from GPS to nuclear energy. Einstein's special relativity is not just an academic curiosity. It has had a profound impact on our technology and understanding of the universe. GPS satellites rely on corrections from special relativity to maintain their accuracy. Particle accelerators, used to study the fundamental building blocks of matter, would be impossible without the principles of special relativity. Furthermore, special relativity laid the foundation for Einstein's later theory of general relativity, which describes gravity as the curvature of space-time. This theory has revolutionized our understanding of black holes, the expansion of the universe, and the very nature of gravity itself. Beyond special relativity, a glimpse into the future. While special relativity has been incredibly successful in explaining the universe at high speeds, it is not the final word. It is incompatible with quantum mechanics, the theory that governs the subatomic world. Physicists are actively searching for a unified theory that can reconcile these two pillars of modern physics, perhaps in the form of string theory or loop quantum gravity. Einstein's special relativity was a monumental leap forward in our understanding of the cosmos. It revealed a universe far stranger and more wonderful than we could have imagined, with implications that continue to shape our technology and inspire our imaginations.